exponential functions. Exponential functions have the variable as the index. So right here is the variable, and the base has to be larger than 0. So when we are looking at exponentials on a Cartesian plane, for y equals a to the power of x, asymptote is always going to be at y equals 0. Domain is infinity, range, it doesn't touch 0, so don't forget the soft bracket, 0 to infinity. And we've got the y-intercept, which is 0, 1, because anything to the power of 0 is going to be 1. Also, when we are doing exponentials, we need to mark another point on the graph, as I did here, because we need to be able to tell the difference between different exponential graphs, and they all kind of look the same. So we need to go over some patterns. So first thing we're going to do is the constant term. Now remember, the constant term moves the graph up and down. So when we have the constant term as 2, so plus 2, we're going to move the whole graph up 2 spaces. So that's the one in red. And don't forget, the asymptote moves along as well. So the asymptote is going to be somewhere like that. So asymptote is going to be at y equals 2. If the constant term is -3, then the whole graph goes down 3 spaces, including the asymptote. So asymptote at y equals -3. Of course, the y-intercept is also going to change. So from 0, 1, it moves up to 0, 3, and the other one goes down 3 spaces to -2. All right, I use this K symbol here, so that amplifies the steepness. So if the K value is 5, then everything's going to be 5 times greater. So here's a normal graph, 2 to the power of x. 5 times 2 to the power of x, it's going to be 5 times larger, so every point is going to be times 5. Don't forget, we always do index first. So if you see something like k to x, we're going to do the 2x first, and then multiply by k. Same thing with this example. You're going to times it by 1 over 3, so it's going to become more flatter. Y-intercept's going to change, and graph is more flatter. Now, if we have adding or subtracting something from the index, we are moving it side to side, left and right. It's kind of like phasing, if you remember in trigonometry. So basically, what we have to do is for y equals 2 to the power of x plus 1, we need to find where this equals 0. Because when that equals 0, y equals 1. So for the first one, we know that x has to equal -1 for it to equal 2, 0. That means 1, or other way around, -1 and 1 is the point that we're looking for. If in this case, x minus 3, that means x has to equal 3 for that to equal 0. So then we get this point. So by looking at this point, where the y-intercept should be, we know that the graph is moving left or right. Everything else is the same. Now, you don't need to put a y-intercept for here or here because it is kind of difficult. So what we usually do is we put one point and we put another point. Actually, this one's quite easy. This one would be 0 and 3, I think. and this one would be 4 and 3 again. Alright, now y equals a to the power of x plus b. Now this is kind of like phasing when we did it in trigonometry, how we slide the graph left to right. So essentially, let's say we have 2 to the power of x plus 1. We know that when 2 to the power of 0, y equals 1. So we need to make that into 0. So when x equals negative 1, we know that x plus 1 equals 0, and y is going to equal 1. So we have a point right here, which is equivalent of 0, 1. So we know that the whole graph has moved to the left. In this equation, y equals 2 to the power of x minus 3. X minus 3 equals 0 when x equals 3. So that means when x equals 3, y equals 1. And we got this point here. So we know the whole graph has moved 3 spaces to the right. Now don't forget, we need to put another point. So since 0, 1, the next one, 2 to the power of 1 is 2. So 1 and 2 I should have put. So the same thing here, we're going to have to put y-intercept here, which is going to be 0 and 2. And here it's going to be 4 and 2. Everything just slid across left or right. Okay, now reflections. We're going to do actually 2 reflections and a combination of the 2 as well. So first of all, y equals negative a to the power of x. Don't forget, we do the index first and then the negative. Essentially what we're doing is we find a to the power of x and then flip it over the x-axis since it's the negative. So 0, 1 becomes 0 to the 0 and negative 1. 1, 3 becomes 1 and negative 3. We're doing y equals 3 to the power of x. So we're just going to flip it across the x-axis. Y equals a to the power of negative x. Same thing as the previous slide, but we are going to flip it over the y-axis. So what we are doing here is, let's say we're doing y equals 3 to the power of x, and y equals 3 to the power of negative x. If x is 1, then it's going to be 3. So we got this point right here. Now, if we want for, in this equation, if we want y equals 3, then this negative x is going to have to equal negative 1. Then it equals 3. So we get the equivalent point on the other side of the y-axis. So everything is flipped across the y-axis. And now we are doing the same thing, but twice. What we're doing is we get y equals 3 to the power of x. We're going to flip it to the other side and then flip it again. It doesn't matter which order you do it in. So we get this graph here. Then I'm going to change that to negative 3 to the power of x, which is going to look like this, except it goes through this point. Then I change it to power of negative x, which then is going to look like that. So you flip it and you flip it over to the other side again.